Please join me in welcoming to the Distinctive Voices podium, Dr. Daniel Swain.
Just bear with me while I get this up here. It's a fun exercise every time I go anywhere to give a talk, getting the microphone up to 6'4" level. Well, thank you for that introduction, and it's good to be here. I've been coming back and forth to Irvine for different reasons for now, better part of 15 years, so it's nice to be back. And thanks again for the invitation to speak here this evening. I know there's a fair number of folks joining online as well, so great to see the turnout. And I think this is a topic of considerable interest for a variety of reasons right now, increasingly as we experience our warming climate, and in particular in California, since I know this is probably a very California-weighted audience, even the folks online. It's been a decade or so of pretty substantive hydroclimate whiplash in this part of the world. This has been a particularly pronounced period in this region of exactly what I'm going to talk about today. So without further ado, I thought it's always nice to offer a brief overview of where we are right now with climate change, because it's something that is always evolving year by year and decade by decade. The Earth, of course, is warming, the Earth's atmosphere, the Earth's oceans, and the rest of it. But the reason I'm here tonight to talk about something other than just rising temperatures is that the main reason we care about that rise in global mean temperature is actually everything that is related to that global mean temperature, but isn't that statistic in itself. So the global mean temperature is just a heuristic. It's just an indicator of all the other stuff that we actually care about in the context of a warming climate. And the warming we've seen is caused, of course, by the accumulation of heat-trapping greenhouse gases in the atmosphere, carbon dioxide chief among them, but there, of course, are others. And human activities are, in turn, responsible for that accumulation of heat-trapping gases in the atmosphere through things like fossil fuel burning, but also land use change, and it isn't just one thing, it's actually a laundry list of reasons why we've produced this accumulation of heat-trapping gases in the first place. The Earth has warmed, if we use decadal averages, which is probably what we should be using if we want to talk apples to apples with things like the IPCC. You hear those numbers, those 1.5 degrees Celsius, 2 degrees Celsius targets. Those are long-term averages, so on that apples-to-apples basis, we've warmed about 1.3 degrees Celsius so far, but the last couple of years in particular have been quite a bit above that on a global average. You may have heard that we've seen record warm temperatures globally the past couple of years, and that means that we have seen the last 2 years have individually been above that 1.5 degrees Celsius level. We're currently still on a path to about double that amount of warming that we've seen so far. So on track by the end of the 21st century for somewhere between 2.5 to 3 degrees Celsius of warming, which is a lot of warming, and the impacts from that second increment will be a lot greater than the first. But the last thing I wanted to point out, and this is a map that I update every year when I recreate a version of this slide, but the map that you see here is valid through 2024, so this is the most recent full year we have available. And I just want folks to notice that not so much the details on this map, but that, first of all, it's all yellow, orange, and red, meaning that pretty much the whole world has warmed to some degree. There really aren't any places anymore that haven't warmed at least a little bit. But also that the spatial pattern is highly variable. The Earth is not warming evenly everywhere, and there are some coherent spatial patterns for fairly well physically understood reasons. For example, the continents are warming faster than the oceans, and the Arctic, that big bright red blob at the northern end of the planet, is warming faster than anywhere else on Earth. So these are sort of the fingerprints of human-caused climate change that actually helped us understand and confirm that it was in fact human activities that caused it, because other types of natural warming would have a different spatial pattern. So this sounds like a very technical slide, and if you dig into the details, it is, but bear with me for a moment, and I'll explain why I started off with something that looks so technically scary. In the planetary greenhouse that we all live in, there is a relationship known as the Clausius-Clapeyron relation. My French is not very good, so literally in this case, so excuse me, but the idea here is that the saturation vapor pressure, so the amount of water vapor that can be in air, increases exponentially as the temperature of that air rises. And here I am speaking in technical terms, not figurative ones. By exponential, I literally mean an exponential function, mathematically speaking. So for this reason then, global warming, which of course is raising the temperature of the atmosphere, brings about a nonlinear, exponential increase in the water vapor holding capacity of air in general, all around the world. So the short version, I guess, is warmer air equals thirstier air, or a thirstier atmosphere overall as it gets warmer. And this is a relationship, by the way, hearkening back to the name, Clausius and Clapeyron, that goes back to the mid-1800s. So actually, this is not something that you necessarily need a fancy 20th or 21st century mathematical climate model to understand. This is the background for this is essentially laboratory science from well over a century ago. As it turns out, climate models emergently reproduce this behavior, and now, as we've conducted this uncontrolled experiment in the real world, we now also see this in observation. So this is something that's really well understood, and importantly, we understand why we've predicted it correctly, because the theory and the observations and the models are all in alignment here, which is not true for every aspect of climate science, but it certainly is for this. Because of its importance, and I'll get more into its importance in a moment, my colleagues and I have termed this effect, I don't know if Clausius or Clapeyron would have agreed with this particular simplification, but we've termed it the implication of this increased vapor holding capacity of air, the expanding atmospheric sponge effect. So imagine an ordinary kitchen sponge, literally like the one pictured here that I grabbed off of a discount store weekend ad, and then imagine with several degrees of warming that sponge becomes much larger, comically oversized even. I've actually done this on camera. You can literally find comically oversized kitchen sponges and demonstrate this, meaning that the analogy works more literally than you might expect. But as that air warms, that atmospheric sponge figuratively becomes larger, and therefore the ambient air becomes, if you will, spongier. And the reason why this analogy works pretty well is that it works bidirectionally. So a larger sponge has the capacity to absorb more water, but it doesn't necessarily have more water in it unless there's more water to absorb. Much like the warmer atmosphere does not always have more water in it unless there is water available to evaporate into it. Similarly, if there is water available in that warmer atmosphere, you can have two completely saturated sponges, the larger one holding a lot more water than the smaller one, but unless you wring them out, you aren't going to have that water spill out of the sponge. Much like a moister atmosphere doesn't necessarily produce more extreme precipitation unless conditions are actually favorable for that water to fall out of the air as precipitation. So in practice, what this means, the expanding atmospheric sponge effect, which comes from fairly basic thermodynamics that we've known about for a better part of 2 centuries, raises the ceiling on precipitation intensity, not necessarily the overall amount of precipitation, but the ceiling on how intense it can become at its most intense, but also on evaporative demand, which is essentially the opposite of precipitation. So the potential maximum intensity of evaporation and precipitation both become exponentially greater with linear warming. That's the basic science behind the expanding atmospheric sponge effect. So in practice, think heavier downpours, but also greater atmospheric thirst. And the net result of this is something that my colleagues and I have called, in only marginally more scientific lingo, hydroclimate whiplash. So we wrote a review paper earlier this year on this because there were lots of disparate threads in climate and atmospheric science and earth system science connecting different pieces of this. And none of this is anything that we've personally discovered, but we're trying to put it together into a more coherent framework using this hydroclimate whiplash framing. And when we do that, we find that there is strikingly clear evidence that it increases almost everywhere in the world as temperatures go up, particularly over the continents, partly, as I noted in the first slide, because the warming itself is faster over the continents. And between about 1 and 3 degrees Celsius of global mean warming, we find that the rate of increase starts to accelerate. Now remember where we are now. We're right smack dab in the middle of that range, and we probably will be for most of the rest of our lives. So we're in that period of acceleration right now. And so this is really, in practical terms, the combined effect of this increased ceiling on how intense precipitation can become on the one hand, and the increased ceiling on how evaporation can become the evaporative demand on the other. So why do we care about this beyond the interesting science that goes into it? I think increasingly my inclination maybe is to flip the question and say, why wouldn't we care about this? But let's just go through some pretty dramatic examples. This is a slide that I created before we even coined the term, by the way. We were trying to decide what to call it, but this is just one example of something that happened in Southern California, where we went from an extremely dry period in the autumn and early winter months in 2017, which culminated in what was then the largest fire in contemporary California history. That's now been eclipsed, I think, 5 times since 2017. This was the Thomas Fire, which was devastating locally, but perhaps even more devastating for folks in Santa Barbara County and in the community of Montecito in particular, was the catastrophic debris flow that followed when a ½ inch of rain fell in about 5 minutes. On that burn area. But the reason I raise this as a pretty dramatic example of a dry to wet whiplash is that if you take the average of conditions between December and January, that 60-day window, you might calculate that on average it was mostly sunny and breezy with below average precipitation, which I think is pretty clear it doesn't really capture anything that mattered during that period. So if we only consider changes in the average, then we're often going to miss the point. We're going to miss the critical stuff that actually is absolutely essential to understand if we want to have a good handle on what a warming world will look like. And there's a bunch of other examples with this as well. We have case studies from any number of California counties and regions, and I just keep adding more and more panels to these as the years have gone on. And we go, these are in Northern California. You can kind of see this remarkable alternation over the past, I guess it's more than 10 years now, 15 years, let's call it. But we see this too in Southern California as well, and a similar pattern where we've had some pretty dramatic swings, and in some of these places I could even add yet another image that I just didn't have time to add just from the past 12 months here, and actually I will get to that in a moment. So what's going on here in California? California is a hotspot of hydroclimate variability to begin with, and it feels like something maybe different already here. Well, it isn't the overall average precipitation, and it hasn't really shown much of a trend, believe it or not, over the past century or so. Which some folks have taken to mean that nothing is changing at all. But as I'll show you in a moment, that couldn't be further from the truth. Because what we have seen is an increase in the variability of moisture. So this is the combination of precipitation and evaporation and its variability. And if you take a look at it over the same period, the precipitation has neither increased nor decreased. The variability of moisture certainly appears to have increased overall. At the same time, we've seen a very strong increase in the frequency and severity of drought. Again, this is the same location and the same period during which we've seen no large decrease in precipitation. So what's going on here? What's driving it? Well, given the subject of this talk, I think you have a sense of where I'm going with this, but let's dig into it some more. California's climate is actually quite unusual in the context of North America and even globally. And you can see this, at least in the context of the lower 48 states, In this map on the right, showing essentially the amplitude of year-to-year precipitation variability. The units here aren't super important. I just mostly want you to see that California is in different colors than the rest of the country, and Southern California in particular is distinct even from Central and Northern California. So Southern California has the highest interannual precipitation variability of anywhere in North America and is really high on the list globally as well. We also have a really strongly seasonal cycle of precipitation, which for anybody who's lived here for more than a couple of years is very obvious. The summer is dry, the winter hopefully is wet, and the autumn and spring are transitions that can be wet or dry depending on the year, but in general it's wet winter, dry summer is what's reliable most of the time. And the reason for that is that California exists at a climatological margin between the stable subtropical regime to our south that often encompasses southern and central California, and the more active, unstable mid-latitude climate regime to our north. Think the Pacific Northwest, Canada being the more classic examples. And the reason that we have such a strongly seasonal cycle is that the jet stream, which dictates essentially the latitude of the storm track, it oscillates from season to season. It's further north in the summer, which keeps us dry. It still rains up in Vancouver and Seattle in the summer, but not in California. In the winter, it sinks southward, and we actually are more in that mid-latitude unstable regime. So this is not a fixed boundary. It oscillates season to season, so that's why we have dry summers and wet winters. It oscillates year to year. It's why we have some really dry years and some really wet ones. The jet stream can be further south in some winters than others. And it can even vary a lot within winters. We have midwinter dry spells, sometimes that last weeks at a time, and those usually tend to be when that jet stream is farther north and we're more subtropically inclined. And all of this leads to high variation in season to season, year to year, and even within seasons. That also leads to pretty high drought susceptibility because we only really have a single opportunity to get the water we need in any given year in California, unlike other parts of the world where it can rain in the summer or the spring just as much as it can rain in the winter. If it doesn't rain here enough in the winter, we're sort of out of luck, essentially, until at least the following winter, because we know we're not going to get, except in some very unusual circumstances, a significant amount of summer rain. There have been a couple of recent summers in Southern California where there has been fairly anomalous out-of-season rain. That's a whole nother interesting scientific question, but it remains the case that today and even in a much warmer future, we'll still have a predominantly wet winter, dry summer type climate. But what will that future climate look like with respect to precipitation, wetter or drier? And it's a question that I, as a climate scientist, can't answer, which makes people very concerned about the business. But then what I really point out is that we haven't seen a large increase or decrease in precipitation, but that's actually consistent with what climate models say. They don't really agree on the sign, S-I-G-N, meaning plus or minus, in terms of what California's annual average precipitation will look like in the future, but they do agree that the variability will increase, and in particular, they show a large increase in both wet extremes and, to a lesser extent, although in Southern California it really is a mix of both, dry extremes as well. So it turns out that the climate models are not really saying that precipitation isn't going to change. What they're saying is that there's going to be more whiplash, more variability, and that if you look at the long run, the amount that you see the increase in extreme wet events and extreme dry events mathematically cancel each other out. But in practice, of course, any given year, you're not experiencing the average, you're experiencing one of the two extremes. And so in practice, it's actually very important to distinguish between truly no change in precipitation or changes on opposite ends of the spectrum that just mathematically make it seem like, if you don't dig deeper, that nothing is changing. And this is true year to year and also within seasons. We actually find that on an annual average basis, again, these changes aren't huge, but even if you just look at winter, for example, places in California where we don't know if we'll see an increase or decrease in winter precipitation, and honestly, it doesn't look like it's a very large number either way, show huge increases in the month-to-month swings even during the wet season. So months in winter that could be completely dry, followed by months that are some of the wettest that we've ever recorded. And yet another dimension where this pops up. Again, this is all emergent behavior in climate models, which is really quite striking, is that we already have, of course, a very sharply seasonal rainy season, as I mentioned, wet winter, dry summer, with some shoulder seasons that can kind of go either way. Well, moving forward, it looks like those shoulder seasons, this year maybe not the best example of that in Southern California, but we generally expect to see that the shoulder seasons will become drier, but that the core winter rainy season may be a bit wetter. So not only higher year-to-year variability, but a further accentuation of that already short, sharp seasonal cycle. And that, of course, has a lot of implications, in particular for things like wildfire risk, but also for agriculture, for snowpack, really anything that we care about that relates to water, snow, and fire in California. And on the wet side of things, what this looks like, as you may have heard, are stronger, moister, what are known as atmospheric river storms. These are California's water delivery mechanisms, these corridors of highly concentrated atmospheric water vapor moving quickly in the air, pushed by strong winds in that column of air above your head. We actually had one today up in Northern California and the Pacific Northwest. And they occur every winter. In fact, in general, there are usually somewhere between 1 and 3 dozen atmospheric river events somewhere along the U.S. West Coast every winter. So they're not rare unto themselves. But when they are extreme, they can be really disruptive and even damaging. And almost all of California's most significant flood events have been caused historically by particularly extreme atmospheric rivers or sequences thereof. They're also the main mechanism, by the way, where we get most of our water supply. So they're a blessing and a curse, depending on the context. And if we didn't have them at all, we, of course, would have no water. So we shouldn't wish for these to go away, but also we do need to be wary about their most extreme form. And that is precisely what we expect to increase the most in a warming world. We do not necessarily expect to see more atmospheric rivers. In fact, we may even see, some evidence suggests, fewer of them, but the ones that do occur will increasingly be of the more extreme variety, delivering larger volumes of water more quickly and more intensely. And California does have a longer history of severe flood risk than I think a lot of folks necessarily realize, partly because the last really big one was, I don't think there's anyone here in the room today who was alive when the last one occurred in 1862. We really haven't had a statewide flood of this magnitude. There have been big regional floods, but nothing on a statewide basis. Really, this century, you have to go back well over a century. The timing of this, actually, when it did occur in January of 1862, was such that Governor-elect Leland Stanford, this was the inauguration day when the floodwaters rose most suddenly in Sacramento, and he had to return following the ceremony, which was cut short to his home via the second-story window after having walked out the door the morning of the ceremony. That's how quickly this flood developed in Sacramento. And there is evidence that these floods of these magnitude occur every 1 to 200 years. So they're rare in the context of any individual human lifespan, but they're not rare in the broader geophysical Earth history scheme of things. These are quite regular events. Well, they're not regular in the sense that they're periodic or on a particular cycle, but they're not exceptionally rare in the context of millennia, for example. You'd expect 10 to 20 of these in any given millennium. Obviously, a modern-day repeat would be a big problem for modern-day California. In 1862, California was home to around 400,000 people. I think there may be more people than that in a 10-mile radius of where we're currently sitting. So it's a very different world with 40 million people in California today versus 400,000 the last time we had an event of this magnitude. And our own research suggests that there is a greater than 50% chance that we see an event this big in the next 40 years or so. And that doesn't mean it's going to take 40 years to get there. That means the cumulative likelihood is about that high. It could happen in any given winter. Of course, that was already true before climate change, but our research suggests that we've really upped the ante. In the background, in the last century, even as during this window where we've been more concerned with severe droughts and wildfires for understandable reasons, because we've experienced those very acutely in recent years, But this is a risk that we think has quietly increased in the background due to the expanding atmospheric sponge effect. For better or for worse, our particular iteration of that expanding sponge in California in the last 10 or 15 years has been on the dry side of things. But that pendulum will eventually swing back in the other direction by virtue of the basic thermodynamics of that expanding atmospheric sponge. By the same token, and we've already seen this, so this is always a bit of an easier sell, unfortunately, to folks in the Southwest and California, that we already are seeing worse droughts. The same amount of rain and snow doesn't go as far as it used to. And that's not a statement, by the way, about human use of water. Actually, per capita water consumption is going down in the West and in California. So this isn't a statement about how we use more water than we used to. This is a statement about how just if there were no humans, if it was just the pure geophysics, this water wouldn't be producing the precipitation we're seeing wouldn't be producing the same runoff that it used to, because that expanding atmospheric sponge is demanding more of that water back from the land surface, from those bodies of water, and is evaporating it back into the atmosphere. So we see more precipitation on fewer days, so more dry days in between. There's the issue of snowpack, of course, which is declining for the fairly obvious reason that snowpack is harder to accumulate once you're above the freezing line more often. But the one way to think about this is that as recently as 40 or 50 years ago, droughts could be hot or they could be cold. You could get cold temperatures and below average precipitation co-occurring. California did at multiple times in the 20th century. But now, by virtue of it being warmer than average pretty much all the time, virtually all droughts are coinciding with above average temperatures. So the short version is all droughts are hot droughts now. And so now temperatures are always aggravating any given precipitation deficit. Again, blame the dry side of that expanding atmospheric sponge. This is true of precipitation in a broader sense. And I've been talking a lot about California, and this plot on the left is a little difficult to interpret, so don't worry too much about the details. But the point is, this is happening in a very general sense. In fact, it looks like on more places than not that we see this compensation effect, essentially, where there are large, even very large increases in the very heaviest downpours on Earth at the expense of the weak to moderate events. So the gentle rain and the drizzle, that starts to go away, and you just start to see what remains are increasingly heavy downpours. This is something that climate models suggest. It's also something that we're starting to see again in observation. So think of this as, it used to be a saying that the wet places would get drier and the dry places drier in a warming climate. And we've kind of updated that paradigm from 15 or 20 years ago to move from the spatial sense to the temporal sense and say that the wet times get wetter and the dry times drier, because this applies almost everywhere. And it isn't so much about places that are dry to begin with getting drier. It's whenever it is dry in a given location, even if it's a wet place on average, those will be drier. And the same is true of wet conditions as well. So really, just to extend a common saying, when it rains, increasingly it pours. And this is true, by the way, when it comes to things like flood risk as well. And this is a bit of a pernicious issue, because what we see with broad global increases in the most extreme heavy downpours, which are largest precisely for the most extreme events, we actually see decreases in runoff and decreases in floods for the most commonly observed kind of events that occur every 5 or 10 or every 20 years. So the kind of events we have the best record for. We got about a century of flood record keeping. And so when we're talking about a flood that might occur every 10 or 20 years, we've got, 5 or 10 observations of events like that. But for rarer events, for floods that might only occur every 50 or 100 or 200 years, we don't observe those very often by virtue of their rarity, and yet it is precisely those kinds of rare but high magnitude events that we would expect to increase, because we have, again, a compensation effect. The expanding atmospheric sponge dries out soils most of the time, on average. It actually gives those soils more capacity to absorb the water that's coming from heavier downpours up to a point. And this is the key. Below that point, you actually see drier soils that have a greater capacity to buffer against flooding. That's why we see decreases in small floods. But once the soil's saturated, now it has no more capacity to buffer against the heavy rainfall. And so above a particular threshold, that's where we see the increases in the most extreme floods as well in our predictions about what this looks like moving forward. And you can see why this might be a problem, because it's been really difficult to detect historical increases in floods. But the reason for this, we think, is probably because we're mostly observing those 5, 10, 20-year floods that occur more frequently by virtue of only having 50 to 100 years of record. And it is precisely the rarer ones that we don't observe very frequently that probably are the ones that are going to increase the most. This leads to some pretty significant challenges from a communication and climate adaptation perspective, because if the things that we're observing are not increasing or even decreasing, but we're telling people that you really need to be preparing for worse floods, that's a bit of a hard argument to articulate in practical terms. So the physics of whiplash, of these compensation effects, these compensatory sort of effects on opposite ends of the hydroclimate distribution make things pretty complicated in practical terms. And I'll get to wildfire now, because I think this is something that's, of course, top of mind, especially in Southern California after the year we've had in 2025. We have seen, and this is a paper that came out in 2021 using data up through 2020. This paper would actually be even starker if we had the last 4 or 5 years of data included in it, but it gets the picture across, which is that this is not just a Western United States issue with wildfire. When you look at the kinds of weather conditions that are conducive for extreme wildfire behavior or fast-spreading intense fires, everywhere that we look, there appears to be an increasing trend. So it doesn't mean that there's a large increase in extreme fire weather on every square inch of the Earth. But the main idea here is, if you look at this global map that's up on screen, look at all the areas that are orange and red, which are common on every continent except for Antarctica somewhere, and look for the blue areas. And I challenge you to find them, because there essentially aren't any. And the reason for this, the reason why there's essentially no decrease in extreme fire weather conditions anywhere in the world, is because of, you guessed it, that expanding atmospheric sponge. The increasing evaporative demand means that in wildfire-prone areas, you're seeing drier conditions all the time, and in places that were not so historically wildfire-prone, you're seeing not necessarily drier conditions all the time, but when it is at its driest, it is even drier than it was. So the driest gets drier. That's what's going on with wildfire. And in California, we've seen this quite dramatically. This plot was updated only through 2018 when we wrote this paper, and of course, if we extended it a few more years, this continued. This really comes from a pretty basic reality, which is that what is burning in a wildfire? It's vegetation, it's biomass, it's plants. And plants are part of the biosphere that depend on the soil. And where do plants primarily get their water? Through roots from the soil. So what's going on here is that the fuel for wildfire, which is plants, either living plants or dead plants, as the case may be, or dormant plants when you're sort of in between. Think about those fall leaves or that winter dormant vegetation. As the atmospheric sponge demands more water from the landscape, it also demands more water from the soil, which depletes soil water for plants, and then even from plants directly, both living and dead. And this is essentially the main connection between climate change and wildfire, is via the expanding atmospheric sponge, the dry side of it in most cases, making the landscape either drier on average in some places, or in wetter places, making the landscape drier when it is already at its driest. And we've seen this in California, where the frequency of extreme fire weather conditions in autumn in particular has already greatly more than doubled over the past 40 years. So this is not a small or subtle change. If things feel like they were different from 20, 30, 40 years ago, they absolutely are. And this is one of the more dramatic examples that we find, actually, of things that have changed so quickly in recent years. And the reason for this, once again, is because the underlying relationships are not linear. They are, mathematically speaking, exponential. We see that the level of vegetation dryness, so essentially its aridity, is exponentially related with the intensity and size of fires. So this is a little bit concerning when we think about what we're seeing with this expanding atmospheric sponge. And I think I don't think I need to motivate this particular part of the conversation to anybody in the room, because everybody has lived this sequence of events. But I did want to talk a little bit about how in Southern California there's yet another piece to the hydroclimate whiplash puzzle when it comes to wildfire, and how it's not simply a case of drier equals worse fires. There's actually a twist here that I think has become really apparent after what happened over the past 18 months. So if you remember, much of 2023 and 2024 in Southern California were really wet. In fact, in some places seeing a near record wet 2-year, 18-month period from 2023 into 2024, particularly in LA and Orange counties. But then that was immediately followed by the driest 6 to 9 month period on record from summer through early winter of this year. So essentially from June of 2024 through the first half of January 2025. And then we had an extraordinarily dry and warm period for a couple months in there in the middle. We had that really late onset to the rainy season last year. It did not rain at all until after mid-January in Southern California last year, which is really late to have gotten nothing at all. Fortunately, this year, of course, we've already seen significantly more precipitation than we saw last year all the way through January. But it was this sequence of events that was particularly striking, because when Southern California is wet, think about what the primary vegetation is on a lot of the coastal hills. A lot of it is chaparral, so it's the shrubs, and it's grass. And grass in particular is very responsive to moisture. It grows when it's wet, and it doesn't grow when it's dry. Just think about a well-irrigated lawn trying to keep up with the mowing versus sort of neglecting or killing your lawn on purpose during a drought. You don't have to mow it anymore, it stops growing. Same thing is true in the natural world. So this particular sequence of events, from near record wet, or in some cases record wet, to then record dry immediately thereafter, that 1-2 punch of extreme wetness to extreme dryness led to an episode of exceptional vegetation and biomass accumulation, immediately followed by the most rapid and most profound vegetation desiccation period that we've seen in the recorded record in Southern California. That was a really alarming sequence of events that had a lot of folks pretty concerned in the meteorology and fire world last November and December, and then into early January. And then, of course, we all know what happened when those very strong Santa Ana winds came in January with the devastating LA fires. Just a bit of further context about what we see in the long-term trend in Southern California. And again, these are not climate model predictions. These are just observations about what's occurred. We see that, again, that variability is the thing that creeps in. And we've seen about a 25% increase in the late season moisture variability in the fire zones from this year in Southern California. So this is a substantial increase in precisely that kind of whiplash that we're talking about. This has essentially been driven primarily by an increase in the prolonged dry period. So in this case, we've seen essentially no decrease in the wettest wets. We haven't yet seen an increase in the wettest wets, which is interesting. I still think we will eventually. But we've also not seen a decrease in them, but we've seen a large increase in the driest dry. So if you keep the ceiling at the same point and then start dropping the floor, the gap is still widening between them. That's what's been happening in Southern California so far. And we've also seen an even larger 36% increase in the severity of the worst fire weather conditions during winter for November through January. And this is a season that hasn't been studied as much as fall and summer because you don't think about it as much, but you can still get significant wind-driven Santa Ana wind-driven fires in Southern California this time of year. And in particular, it matters if the rainy season is delayed, as it was last year, because we do not have any moisture to tamp down that fire threat. So that's in itself a pretty significant increase. And an interesting paper came out just 2 weeks ago. I was not involved with this work, but I found it really interesting because it really illustrates this. And all you really need to see without, don't worry about squinting too much, but on this plot, it's going backwards in time from the point of fires in different California ecosystems, where 0 months on the right is essentially when the fire occurs, and you can see the numbers to the left. Those are months in the past, so 5 months, 10 months, up to 30 months in the past. And brown colors mean dry, and green colors mean wet. And what you see is that, of course, right around the time of major fires in California's Mediterranean biomes, these ones that are home to primarily shrubs, chaparral, and grass, what you see is that it's really dry when the fires occur. No surprise there. But look at what happens about 15 or 20 months before. It's not dry the whole time. There is this wet to dry cascade that is a signature. So you actually go from a year to a year and a half before a active fire period from extreme wetness and cascade very suddenly to extreme dryness. And 2025 was the single most extreme iteration that we've seen of this in California's historic record. But this is not an unusual pattern per se. This is in fact the signature of the most severe fire periods in California's Mediterranean grass and shrub-dominated ecosystems. In forests, by the way, anybody have any inclination as to what that might look like? That's maybe a simpler picture, where the longer your drought, the drier it is, the drier the forest. But the more flammable it becomes, the more fire activity you see. And the reason for this is essentially, in a forest, you can have a dry year, you can follow it by a wet year or a dry year. The trees aren't coming and going year to year depending on how wet or dry it is. The trees are there. Drought, flood, whatever. They're going to stay around for decades, for centuries, sometimes even longer. But the grass, the shrubs, those really do come and go. You can have grass that grows a lot in one year and not at all the next year. And same is true to a lesser extent with the faster responding shrubs. And so the reason why this cascade matters in these specific ecosystems is they're very responsive to moisture levels. And so what we see is that this pronounced whiplash effect is maybe even more important in places like coastal Southern California than almost anywhere else. So I want to leave with a few parting thoughts, since I know, and I also want to leave time for questions, both from the folks live in the audience and then maybe even a few from those joining online. Hydroclimate whiplash is maybe a term you haven't heard before. But it's not really a new idea in climate science or atmospheric science. In fact, we're really just drawing together some disparate threads from different fields that have been around, in some cases literally for 150 years or more. There's really clear evidence that this is something we're going to see increase in a warming world, not just in California, but globally, although California may be one of those global hotspot region. And think of it not in terms of whether a place is getting wetter or drier on average, but in many cases the answer is both at different times, whether you're a wet or a dry place to start with. And again, you can blame the expanding atmospheric sponge, or if you really want to, you can even demonstrate this effect in your own kitchen using two differently sized sponges. And why does this all matter? Well, hopefully it's pretty clear why this is all really important for our own day-to-day lives as well as scientifically. But the main reason I think it matters as a climate scientist who speaks a lot with people in the policy world and people who operate dams and who are designing infrastructure for the 21st century is that you're going to design and operate that infrastructure differently if you think that precipitation just isn't going to change at all, that it's going to be the same repeating pattern of what we're used to historically, versus if you realize that the relatively modest change in average precipitation is actually made up of big, increasingly wide swings on either side of the average. That's a very different world, practically, and it means managing or co-managing the risks of drought and flood. And the reason why it's so important that we recognize this is we might make the wrong adaptations if we make the wrong assumption about the way the world actually is going to change. And so in general, and this is sort of my mantra in climate science, both in this context and in other contexts as well, it really just emphasizes the critical importance of thinking beyond the mean, because, in the Earth system, it's rarely the mean state that's telling us what we need to know about the way the world works, and that shouldn't be any different with respect to climate change. And this is one really tangible reason, hopefully tangible reason, why that's the case. And so that's all I've got for you this evening. As you heard in the introduction, I'm rather accessible online, so you can find me in various places. Also, if you happen to have your smartphone with you, feel free to use or if you're online as well, feel free to take your smartphone out and scan the QR code on the screen to take a survey from the University of California regarding my weather and climate communication activities. I'll leave that up as we have the discussion. Thank you.